Thank you all for watching this video. Today, I'm excited to introduce our work, Route T to I, titled Adaptive Routing of Text-to-Image Generation Requests between Large Cloud Models and Lightweight Edge Models. At its core, Route T to I is a smart routing system that dynamically decides, for each user request, whether to generate an image using a powerful cloud-based model or a lightweight model running directly on the user's device. The goal is to maximize image quality while minimizing computational and financial cost. Let's start with the context. Text-to-image T2I models have made remarkable progress in recent years. Given a natural language prompt, they can now generate highly diverse, visually compelling, and semantically accurate images. However, this impressive capability comes at a price, literally. State-of-the-art models are massive in size, often requiring large memory and significant computational power. As a result, they can only be deployed on cloud servers, which incurs substantial service costs. As shown in this table, in commercial-scale deployments handling millions of user requests per day, the cost of always using the cloud model becomes prohibitively high. One natural solution is to deploy lightweight models on edge devices, such as smartphones or laptops. These models are much smaller, faster, and free to run since they use the user's own hardware. But there's a trade-off. Their image quality typically lags behind that of large cloud models, especially for complex prompts. This leads us to a critical question. Do all user requests truly require the full power and full cost of a large cloud model? Our answer is a resounding no. Consider this simple observation. The complexity of a generated image often correlates strongly with the semantic richness of the input prompt. For instance, a prompt like an apple on a table contains few objects and straightforward semantics. In contrast, a cyberpunk cityscape at night with flying cars, neon signs, and rain-soaked streets demands far more compositional reasoning and visual detail. As illustrated in this figure, for simple prompts, lightweight edge models can often produce images that are visually comparable, or even superior, to those from large cloud models, especially when the cloud model overcomplicates or hallucinates unnecessary details. This insight opens the door to an adaptive routing strategy, intelligently directing each request to the most appropriate model, edge or cloud, based on the prompt's characteristics. In our setup, the cloud model is powerful but incurs both monetary cost for compute and communication latency for data transfer. The edge model is cost-free and low latency but may fall short on complex tasks. Critically, the routing decision is made before image generation begins, so each request is processed exclusively on one side, either edge or cloud, avoiding redundant computation. We formalize this as an optimization problem. Maximize overall image quality subject to a constraint on the fraction of requests routed to the cloud, since cloud usage directly drives cost. But here's the challenge. How do we measure image quality? Quality is inherently subjective. It's not just about resolution or realism, but also relevance, composition, and aesthetics. Some existing works evaluate quality along multiple dimensions. Inspired by this, we define image quality as a multi-dimensional metrics, where each dimension captures a different aspect. We then introduce a comparative framework that evaluates which model, edge or cloud, is likely to produce a better result along these combined dimensions for a given prompt. Now, let's dive into the Route T to I framework, which consists of three key components. Quality evaluation module shown in blue. This estimates the multi-dimensional quality gap between edge and cloud outputs. It is used as the target in the loss function to train the root model, indicated by the yellow arrows. Routing decision engine, black arrows. At inference time, the routing model outputs a predicted quality gap. This is then plugged into our constrained optimization problem, which balances quality gain against cloud usage budget to make the final routing choice. In summary, Route T to I enables cost-efficient, high-quality text-to-image generation by adaptively leveraging the strengths of both edge and cloud models. Routing model, the core intelligence. Given a text prompt, it predicts whether the edge or cloud model will yield higher quality. Here's the innovation. We treat the prompt as a sequence of tokens, the same tokens used in the T2I generation process. Since these tokens interact with image features via cross-attention during generation, we hypothesize that certain tokens are more predictive of quality differences than others. To capture this, we design a token selection gate that identifies for each quality dimension the most influential tokens in the prompt. These selected tokens are then fed into a dual-gate mixture of experts, MoA architecture. One gate amplifies positive influences while the other suppresses negative ones. By comparing these dual signals, the model infers the dominant quality trend, and thus the optimal routing decision. Now, let's move on to the experimental section. First, we present the visualization results. Second, we compare our approach against state-of-the-art SOTE methods. Given the current lack of routing mechanisms specifically designed for text-to-image generation models, we adapted existing LLM router techniques to fit our scenario. Our results show that at a routing rate of 50%, our routing strategy recovers 83.97% of the performance gap between the local and cloud models. Finally, we evaluate the cost savings at equivalent output quality. Specifically, to achieve 50% of the quality improvement obtained by exclusively using the cloud model, our method reduces the number of requests routed to the cloud model by 70.24% compared to a random routing policy. Thank you for your attention.